Okay, so yesterday we went through this. Find the equivalent resistance, showed you that button. Okay, go to that. And we found the total resistance, the equivalent resistance to be 2 ohms. Right? Yes, we went through this, right, yesterday? The 1 over, yes. Yes, yes, yes. All right. Good. Okay, solid. Beautiful. Okay. And so the total resistance was 2. Okay. So what would happen if we added another resistor of 8? Find the equivalent resistance. Go. With your calculator that has a really nice button that makes this easy peasy lemon squeezy.
Maybe your water.
Yep.
Wait, how do you type this in?
You go 12, that button.
And then
that button. No, yeah. Yeah. It's that button or this button, depending on your calculator.
And like how many times she gave you guys to review.
Because I get 1.25. 1.25?
Yep.
8 fifths is 1.6.
So you go 12, that button, plus 6, that button, plus 4, that button, plus 8, that button, equals. And then hit that button again.
Oh, 6. 8 fifths. 6. Or did you just point to it?
I did. Right there.
I got 1.6. Oh my gosh, I'm looking at the yellow writing.
I got 8 fifths, and they got 6.
You're right.
I
One.
got 1.6 is 8 fifths.
Yeah.
Yeah.
Oh, hey! You said 1.6.
Okay. Correct answer is 1.6.
It's supposed to be in degrees.
Doesn't matter. Nope. So, how does that compare to 2? Less.
No, I got 1.6.
Okay.
I get 1.25.
Am I typing it wrong? And then watch, it'll switch from fractions to decimals.
I think you might have
Oh, where'd that come from? I genuinely don't know where that's from. It's the x to the negative 1.
Now hit that again.
So you just do 4, and then you hit the x to the negative 1, and then you
Equals.
And you just
4.8.
I don't hit. I mean,
Because it's easy to change it to it.
so I just do all of them like this. So just do all of them in a line, and then you hit equals, and then he said you hit the button again and equals, and it flips it.
See? It's not just me.
No,
We're getting 4.8 now.
And then you have to flip it
That's
to get
just-
8 fifths.
It's just adding 6s.
Oh, okay.
So hit the button again.
I don't know why he's doing that.
And now hit it. It's
My calculator is defunct.
See if you can get rid of that K. I don't know what
What's
that
the K?
I don't know.
Do you know what this K is at the bottom? K? No.
All right. So here's what proof of concept. With this, the total resistance was what? 2. Adding another resistor in parallel gave us a resistance that was less than 2. Okay? This is because, don't think of it as like, oh, I'm adding another resistor. How does that resistance go down? Think of it as adding another path for electrons to flow, another checkout lane to Walmart, another hole in your water tower. Okay, so there's less resistance, allows for more flow. Okay, the battery now has to supply current for this one, and now this one. So the total resistance, the total current's going up, total resistance goes down.
The way that like more resistors make the resistance go down, does that only apply in the parallel?
Yes, it does. Because as you add more resistors in series, think of your lab, what happened to the brightness of the light bulbs? As you added more, it went down.
So in a series circuit, the more resistors.
Yep. Series makes sense in terms of that. Parallel is the wacky one. Okay? All right. So give this one a shot.
I got it though.
Okay. Thumbs up when you have something.
Yeah.
Okay. If you got B, you forgot to find the reciprocal. Flip it. Hit that button again. Correct answer is A. Okay. Conceptually, here's a way to do this. Ready? The total resistance in parallel will always be less than the least resistor. The total resistance in parallel will always be less than the total resistance, will always be less than the least resistor. Okay? From a Walmart point of view, this is like employee of the year. Beep, 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 beep. Okay? This one is like your grandma's best friend just got hired. She has no idea what she's doing. She doesn't do technology. She wants to show you all her grandkids' pictures. You would not want to be in her line. But is she helping drain Walmart? The fact that she is open? Yes. It's like adding a pinhole leak to a water tower. Not much is coming out, but it's helping drain the water tower faster because there's an additional pathway to get out. Good with that? Okay, junction rule. What this says is the current going in at a junction is equal to the current going out. Okay, so if you have current going in, here's a junction. The current going has to equal the current going out. Think of a river, two rivers, or a creek and a river coming together to make a bigger river. Okay, whatever's going in has to go out. Okay, it's a consequence of conservation of charge. Or if the junction rule, if it's doing like this, if it's like splitting, this junction, whatever's going into that junction has to equal what's going out. The sum of those. You okay with that? So here's a junction. Current's coming out of the battery. That's going into the junction. This is going out of the junction. This is going out of the junction. Tell your neighbor what you think. Yeah, thanks. Have a conversation about physics. Have a conversation about physics.
Well, you ready to see the greatest skier of all time? Who's the one guy in the X Games? Mike really good. Well, I'm basically like Tony Hawk. Watch and learn.
All right, what do you say? Focus. Okay. Applying junction rule says this. The current in is equal to the current out. The current in 1 is going in. The current of 2 and 3 are going out. So that makes, see how I'm applying the junction rule here? Okay. So that annihilates, right? Does that make sense? Okay. This is not series. Current is the same in series, but current is, you add up current in parallel. Okay. All right. So we've got the fact that 1 is greater than 2 and 3. Everybody good with that? Okay. Between 2 and 3, they have the same voltage. So the one that has more current has less resistance. So the correct answer is amazing apes. Okay. Good with that? Learn some stuff? Oh dear. All right. We're going to kick it up a notch.
It's already up.
Oh.
Girl. This is not exactly what it's doing, so it'll get oh. There's so many numbers.
Give me amazing applesauce.
Amazing applesauce.
Why don't they say this like Jeopardy? Like people can buzz in.
Take too long.
Guess the right answer.
Megan.
Maybe
Good question.
oh, but it's choice.
Okay, the question was, how do you know where it's flowing in versus where it's flowing out? The current goes, by definition, goes out of positive into negative. So here's the positive terminal. Out of positive. It has a choice here. It's a junction. Does that make sense? Have a conversation.
So wait, we did all
Yeah.
oh, it goes through 5 no matter. I did it.
Right.
Oh yeah, but we know I actually named dolls. I think Bitsy Daisy.
BBC. 3 definitely equal to 4.
All right. Ready? Okay, so we've already established from the last question that 1 is greater than 3, which is greater than 2. Okay, so now let's look at 4. 4 has to be equal to 3 because there's no other place for the current to go. There are no junctions. What goes in is what comes out. It's just like a river. You can have shallow and deep places, but they all have the same current in that single path. Everybody okay with that? Okay, so 3 is equal to 4. Now, that's a junction. 4 is going into that junction. 2, are you okay with 2 going into that junction? Okay, so 2 and 4 added together give you 5 going out. And here's, just to bring it all full circle, whatever goes into the battery has to go out of the battery. You see that? Does that make sense? 5 is going into the battery. 1 is coming out of the battery. Ditsy daisies.
Yes. Let's go.
Okay? There's no other junction. They can't go anywhere. There's no paths. It doesn't split. Okay? Good? Give me a confidence rating here.
Okay. Like 5 being you're very confident.
Yeah.
1 being like I don't know what's going on.
Yeah.
I'm gonna go middle. I'll go with it because there's definitely still more I could be confident.
Okay.
I think if I stare that long, I'll have to figure it out.
Stare quickly. Because
Please don't add more numbers.
No,
If you add numbers 6, 7, 8. Oh.
Okay.
Oh.
It's only 5 numbers.
But still, look at it.
Yeah.
okay, in your brain. In your brain.
In my brain.
That's a dangerous place.
So the current comes out of positive.
You got it.
Okay, so this is like, say the spring, like the source.
Okay.
Yeah. So it comes down, and here the water has a choice to go this way or that way. So in terms of like pipe size, you're decreasing. So there's more of 1.
1 and 2 are not equal, right?
Because then it decreases because it's
My brain
splitting.
wants to
Yes.
say that.
Okay.
Okay, so does that make sense?
Yeah, that makes sense.
Okay, so this, even though it goes through some kinks,
There's not even an option when it's
when
I
it
know,
gets
I
to
was just
4,
trying to talk myself out of it.
I'm just
this has to be the same because there's nowhere else for that water to go.
Yeah.
Okay, you good with that?
Yeah,
So
that makes
3
sense.
and 4
Mhm.
are the same.
Okay.
And then whatever is going through here is the same here. But then here's another junction.
Uh-huh.
But 2 to get to 4.
So 3 and 4 would equal 5.
2 and 4 equal 5.
2 and 4. Okay.
Yeah, and
Would
4
equal
less
5.
equals
Does that make sense?
Yes.
Okay. And so then you bring it back, and sometimes you describe this as a pump. So it's a whole
Okay.
4 plus
cycle.
1.
And so whatever's going in at 5 has to come out at 1.
Yeah.
Okay, that makes sense.
Good?
No,
I think so.
so.
I think so.
5 is greater than 4.
I know, but there's the junction is where I don't know if 1 and 5 are equal.
So
But they might.
2 and 3 are equal to 4. I don't know. They might be. Just because
I haven't played into it.
like the
Okay, have a conversation if you haven't already.
Because it only gone through a resistor yet. Wait, yesterday didn't you use this color? Equal to 2.
So no, I
Or did you use
5
like,
is greater.
because 5, no. It's 5 to 4, there's no resistor. No, from 5 to 2, there's no resistors either.
Okay, ready?
Blow our minds.
Okay, so we're gonna take this step by step here. You totally should. Okay.
You check your email?
I didn't. All right. 1, 2, and 3 are just individual, the current going through individual resistors. Is everybody okay with that? Okay. So 1, 2, and 3, we can rank those real quick. 3 is bigger, 1, and then 2, based solely on the resistance. The voltage across those are the same. 3 has the most, 1, and then 2 has the least of those 3. Of those 3. That's not the final answer. Okay. That junction has 2 going into it and 3 going into it. 4 is what's coming out. So 4 is greater than 2 and 3. Does that make sense? Here's another junction. 4 is going into that junction. 1's going into that junction. 5 is coming out of that junction. So 5 has the most, then 4, then 3, then 1, then 2. Mega. Yep, totally. So in parallel, voltage is the same. Okay, so they have the same voltage. So if I have more current, I need less resistance. And that's how I did it.
Doing on my own.
Um,
I saw this boy out of
So this is a position.
So
If you look at like 1 and 2, what would make something want to go through the circuit, cut it short to the 80 or go up, or like go to the 70? If that makes sense.
Yep. Okay. Good question. Here's the question on the table. Oh, okay. Why would electrons want to go through this? Okay. In Walmart, you're looking, you're scanning, you're like, which line can I get out the soonest, right? If it has the shortest line, even if it doesn't look like a very speedy checkout person, you're still going to take it. Does that make sense? So there's options. So it isn't like they're like, nope. It's like, if this line is empty, you're going to take it. And so the electrons balance themselves out. Okay, good at that? This got easier. This just got easier. It did. This is an easier question than the previous one. I think you do have it.
Oh, wait a second.
Yes, you got this. This is in your.
We're talking about the resistance little rhyming answers.
Oh.
but added another. No, I just was thinking. So I'm safe.
Correct. Answer is adequate alligators. Amazing orangutans. Okay. Huh. Okay. All right. All right. So is everybody good? There's more checkout lines in Walmart. Okay. We're increasing the amount of people going out of Walmart. Okay. So how is your house wired? Series or parallel? If you turn off your TV, does your whole house go out? No, they're independently hooked up, so they're in parallel. So as you turn on more and more appliances, what happens to the total current? Increases. What happens if you have a lot of current going through a wire? Gets really hot. Why would that possibly be a bad thing? Little fire hazard. Okay. So what do we have that prevents that? Circuit breakers or fuses. Okay. So circuit breakers, I need you to think where your electric panel is. If you don't know, start visualizing your house. It's either in a utility closet, in your garage if you have an attached garage, in your basement. Okay? It's the thing that turns off if you have too many things plugged in. It's the thing that turns off if you have too many things plugged in. Okay, come on back here.
It's a lizard. Oh,
How much snow there is. Scary.
well, it is February 16th. That groundhog said no more.
Yeah, wait, hold on.
Okay.
I hate this 160.
All right. So back in the day, before circuit breakers, they had fuses. Okay, and fuse. There it is. Okay, is if you look in there, there's a green. There, Mitchell. There's a green wire that's in there. That when the current got too hot, that wire would melt and it would blow the fuse. Okay, we still have fuses in our cars. They look like colorful buck teeth. Okay, the part that burns is this Z in the middle in the plastic. You also have some like pill-like fuses that the part that burns is the clear little part in the middle there. Okay, I'm going to simulate this. I'm going to make this my fuse. Okay, and so this is designed to be the weakest link. Okay. Okay. So, oh, that's going too much. That is bright. We're going to bring that down a little bit. Okay. So, as I turn more appliances on, let's see, which one am I going to do here? Here's that. There's that. Why does not turn on? That was weird.
No, did you blow a fuse?
Oh, not what I wanted there. That stays on. This goes to here. There we go. Okay. Now, as I turn on another appliance, okay. Okay. So, as you turn on more and more things, there's more and more current that's going through this first wire. Okay. And the fuse was designed to be the weakest link. It burns the first. Okay. Back in the day, people used to like if they blew a fuse, they'd actually have to like go to a store and buy and put in another, like you burn out a light bulb. And so to like patch it up, if they didn't have it, sometimes they put a penny in place of the fuse, like stick the penny in there. Okay. Why would that be a dumb idea?
It's not gonna break.
Because is no longer the weakest link. Somewhere else, the wiring in your house is now the weakest link of that circuit. Does that make sense? Okay. So if you nowadays you just trip a circuit breaker, okay. So things that tend to trip the circuit breakers are the things that require a lot of current. Those would be anything that heat electrically. Space heater, hair dryer, straightener, okay. Anything that it heats electrically requires a lot of current. Now, an oven, that's on its own separate circuit. A furnace has its own separate circuit. Yep. Because it draws a lot. I mean, it's just, but things that you're plugging into. So let's say you trip the circuit breaker, turn off the other things that went off, and then assumably you want to use the thing that you just turned on. So turn off some other things, then go downstairs or wherever your circuit panel is, find the switch that's in the opposite direction, like all of them this way, and one of them's like the other way, like go, and you're good, and then you can now use your thing, whatever you're trying to use. Okay, good. Have a seat. Thank you.
Yeah, I used to many appliances.
Okay. Okay, we are back to series circuits. Back to series circuits. Here we go. Thumbs up when you have a guess. Have a conversation.
More resistance, decreases current. That's current. Right.
It's actually going to be B. I lied. I looked at the equation. That's my best guess. Is B beautiful buffaloes in Buffalo, New York?
Okay, correct answer is
B. Beautiful baby.
Bouncing butter.
Oh, it's B. Oh.
Crazy cat. Oh, maybe it's all B.
The alphabet soup.
okay. What measurement is the same in series? Current. Current is the same. So to have the most power, what has to happen to voltage? Mathematically, have to increase. So it has to have a greater voltage drop across that resistor. You okay with that? More energy per electron is being contributed to that resistor. So current is the same, voltage is up, so therefore resistance has to also go up. Correct answer is amazing anaconda.
We were all wrong.
Yes, you were.
Wait, aren't you so proud of us?
No. Okay, does that make sense? This is different than parallel. Okay, so the in series, the bigger resistor uses the most energy per electron. It has the biggest in the cascade of slides. Oh dear. It has the biggest drop. It uses the most energy. You okay with that? The lab had identical resistors.
Yeah, we realize that now. That's why we're getting confused.
Oh. Did I not say that in this class yet? I think I did yesterday. Okay.
I forget.
You've said a lot of things.
I did.
What does dissipator mean?
It's the verb we use for power. It means to give off.
Gotcha. So basically, can we just like go home early? I can't focus the rest of the day.
Correct answer is?
Beautiful babies.
Correct answer is 48 watts. I'll give you 3 different ways you can find this. Okay? So, you're looking at the total. So, the total resistance is 12 ohms. Total voltage, 24 volts. So the total current was 2 amps. 2 amps times 24 volts, 48 watts. That's probably the way that I would coach you to do it. Okay? You could, if you wanted to, figure out, there is 2 amps, 2 amps, 2 amps, and figure out your voltage across each one. So this was 6 volts, 8 volts, 10 volts, and 8 volts, and then figure that 12 watts, 20 watts, and 16 watts, and add those wattages up. You could do it that way. Probably the mathiest way, most direct way, is to do, here's a choice for you. Here's some good teaching. Which shortcut power equation would best be employed for this scenario? The right or the left? Which measurement is the same in series? Current. So you're going to pick the left one because you've got this as a fixed value. Does that make sense? So you find the current, you know, is 2 amps. Oh, sorry. That was bad teaching. You could have done it either way. It doesn't matter. You could have gone 24 squared divided by 12 ohms or 2 amps squared times 12 ohms. Either way, it doesn't matter. Okay. Okay, here we go. Here we go. Here we go. Here we go. Okay, okay, focus, focus, focus. I have you for like 5 more minutes. Well,
The problem is that we know every time. Yeah. Like voltage out has to equal voltage in. So if you increase our yeah, but it's not a parallel circuit.
okay. So here we go. So the first thing I need to do is look at the total. As we decrease R1, what happens to the total resistance? Decreases in series. You add them together. Everybody good with that? Okay. The total voltage has not changed because it's determined by the battery. Okay. So what happens to the total current? Increases. So then looking at this individual, the individual resistor R2 did not change. Does that make sense? R2, the individual did not change, but the current went up because the total current goes up, current's the same. So what happened to voltage across R2? Has to increase. Hey. Does that make sense? Amazing apples.
I'd rather not know how any of this works. Don't worry, it's nothing with you. It's the material.
Okay, follow-up question. What about R1? What's the voltage across R1? Yep. We figured out what happened to R2. I want to know what the voltage drop across R1 did. All right. Have a conversation. No, I'll just tell you. All right. So we are looking at this one right here. Okay, individually. Ohm's law in this example fails us because the resistance went down, the current went up. We don't have a variable that's fixed. You don't know with Ohm's law. Does that make sense? Like this could be increase more than that, decreased. That could decrease more than that could increase. They could increase, decrease the same amount. Yeah. Okay. So if you find yourself in that scenario, you need to go to either the loop rule or the junction rule. Those are like foundational. Conservation of energy, conservation of charge. Okay. So I'm going to go to the loop rule. So let's say it's 12 volts, making that up. It's a 12-volt ladder. And originally it was like 8-volt drop and 4-volt drop. There's a slide because it adds up. Voltage gain equals the sum of the voltage drops. Okay. We just said that the voltage drop across R2 increased. So it went from 8 to 9. Therefore, what has to happen, the voltage drop across R1 has to decrease to still add up to 12. Good with that? Okay. Last thing, this is just more practical knowledge. Okay. So let's say, I know you don't use flashlights anymore other than your phone. But let's say you stack batteries end to end. Okay. This is like having two ladders of 1.5 volts. So your drop is 3 volts. Does that make sense? Okay. When you put batteries in nowadays, you arrange them like this. Right? Okay. The battery casing is wired like this, like the springs and whatever. Okay. So they're wired in series. So this arrangement, this device will require 4.5 volts. If you had another one, be 6 volts. Doesn't matter the arrangement, like if you flipped one of these. Yes, it absolutely does. It's like having an upside down ladder. It's kind of a weird thought, but does that make sense? Won't work. Okay, good? That's what today is. Got a worksheet due on Monday. What? The answer to this is D. And then the last one is D again. Dangerous dinosaurs for both of them. Yep.